Good morning. In today's discussion, I would like to start by saying that the supplying of electronic type circuit breakers is growing at an alarming rate out there because obviously, as with all electronics, we see that you get a lot for your money these days in terms of electronics as it becomes cheaper and cheaper. And of course, electronics is impacting on our lives continually in every aspect out there. In fact, it's like the fastest growing, the technology change. In the past, electronic breakers were few and far between, but as the cost of these drop, the actual supply of these type of breakers is a very, very important thing going forward. Unfortunately, when you look at it, not all of the staffing in the electronic industry know how to handle these. So in today's video, I'd like to discuss when you do have this, how you are going to go about setting these. We will have some discussion, and then in following video, there will be an exact example so you can see exactly what we're up to when we have a look and we say electronic type breakers. You can actually see the knobs and get some idea of what we're doing. So today's power engineering topic is the setting of electronic circuit breakers. My name is Kevin, and welcome to the chat. Let's have a look a little bit about the background. So as the manufacturer started making the electronic circuit breakers, they generally started to set these to max. Now they could set them at any value, I suppose, but if they set them to the minimum size, settings, they will get callbacks from the industry as the products don't work, because if people just go and install them and they're on the low end, if you had things like motors, they'll cause immediate trip outs, and then you'll phone them to say the manufacturer's breaker's faulty, come and get your product, it's not working, etc., etc. And of course, to protect themselves, they set all circuit breakers to max that I'm aware of. All manufacturers tend to do that. And it's up to the end user to set these. So it's not really in your interests as a customer to have it at max if you're not sitting at that level from your calculations. At the very least, you could have things like your discrimination fail if you don't set them. If you did not set them according to what the actual site conditions, you could have a short circuit which continued for an excess time and waited until the fault level was far higher than what it initially could have tripped at, and that would damage things like cables, buzz bars. There's mechanical and electrical stresses on components during short circuits, and if you let these go to the maximum all the time, things like the life of the circuit breaker will be reduced quite substantially. And of course, the damage factors are always bigger. There's also the likelihood that possibly the cables themselves could just fuse off the product before the circuit breaker worked. And let's face it, the circuit breaker there is to protect the cables. You don't want that type of activity happening. And I'm sure many of us have examples of where this was never done, and the damage to the panel boards were quite considerable, where they could have just tripped in normality. So the basic approach that we'll use here is something that can be used for all types of electronic circuit breaker arrangements. Now, normally, currently, these are multi-case circuit breakers, where there's quite a lot of activity introducing this type of setting, as well as air circuit breaker types, which have been using them for quite some time. The setting should take place somewhere before the final commissioning and livening up takes place. So these type of things can be done off drawings, if you have consultants that take the drawings and give you the values as a manufacturer from a panel board, and say the following breakers are what I'm recommending for the site, and you preset them at this when they arrive on site. So that's something you can do in a workshop. You can normally adjust all the products in a live state without switching off, and they can be live. Some of the display type electronic unit can actually tell you the value you've set it on by feedback. So in other words, it gives you the feedback on there. Not all of them have that. So you might have to do some calculation in terms of that. If you've got multi-level breakers, of course, you're going to have some discrimination issues, and you need to have a look at that if that is part and parcel. If you've got two ACBs in series and the one downstream should ideally trip faster than one upstream, you need to adjust it for that type of arrangement. And then the major thing here is that you set for the lowest point that you can get away setting the breaker without a trip in the running thereof. So let's have a look. We've got a four-part approach to this. So, and this is a kind of a basic universal all fit type arrangement. And it will work if you know certain of the activities that you're doing and why you're doing them, and you know certain site conditions where you can work them back into this calculation field. So the first and absolute step is to identify the type of load and the amps expected. Obviously, a circuit breaker comes in 1000 amp, 2000 amp, 1600 amp, and preset levels, and not all currents are going to be at that kind of level. So we need to know what amps are typically going to flow in that circuit. If you've got a 1000 amp circuit breaker, that's the maximum current that can be drawn, but it may not be what the transformer or on site can actually deliver. So, and the type of process, for instance, in terms of loads, we talk about things like motor or inrush type levels. Will the actual current increase over time? An example might be a shopping complex starts today, it's all new, hardly any shops in there, and that load might grow over a time period. Or if it's a process, it might be preset to the process. So here you get things like, how can I say, let's say the process uses 800 amps, and it will vary around a certain load and gets to that level. It will never exceed the maximum processing type unless the machinery is then changed. So that's a type of load which is pretty much constant in the background at a fixed level. Obviously, we're looking at things like if the circuit breaker, any circuit breaker that feeds a single motor, might have a fairly substantial dealings with motor inrushes or the type of load that is a single feed system. There's generally a very specific type of inrush capability, or generic loads, general loads like a shopping complex where things are switched on and off all day. They don't generally impact the breaker because they're little motors maybe, and that type of thing. Could also be things on a factory level or a mine. It might be a one mine super motor, 200 kilowatt motor fitted on some ACB, in which case every time that starts, it goes through a cycle of an inrush. We need to know if there's any series connected products in there, because with electronics, we always want the one closest to the short circuit to trip. So inherently in these calculations, we've got to step backwards as we go back to the actual transformer. Are there supply limits imposed by the supply transformer even? You know, we get shopping complexes that are built in stages. And you might only find that only half the transformers are in actual fact currently on that site, and there's no point setting the breaker above all the thresholds of that, and the transformer is at risk of damage. We could set things thumbs up 10% above fixed loads, 20% above more variable type of loads. So we're really going to adjust in the first step, as we said. We're going to look at the amps, because we need to set that amps to realistic values that are going to be on the site. Secondly, we're going to adjust the magnetic trip points or the instantaneous trip points in the light of what we're actually going to achieve in terms of the KA. So we could have a look by measurement and see what the short circuit levels are. We could look at the transformer size and have a guesstimation there. We could be looking at some consultants' drawings. A drawing pack will often tell you what the KA at the certain point is. So the reason we got to look at this is that these values could be anywhere from 4 to 16 times rated current. Now, there already is a link to the rated current. So if the rated current was left at, say, 1,000 amps, but only ran at 800, immediately even these values, which are set to 16 times, would be 16 times the 1,000, when in actual fact, there's only 800 amps. So it's going to be almost 20 times the actual value before it trips. And the transformers may not have that capacity to even trip with the intended short circuit level, which is a fatal thing for a circuit breaker, because the circuit breaker will now be put through a huge long-term short circuit at maximum stress before it trips, rather than have it come out quickly with a short circuit required quicker type of trip. As we said, if it's a shopping complex where they've only put in half the transformers, you will only get half the short circuit initially there. So the drawing might say 30 kA, but you might only have 15 kA initially while phase 1 is there. And then you see there's always this reference back to rated current. Well, a lot of the setting values are some value times the rated value. So that first step is fundamentally the most important step that we will have in terms of the start to this whole process. As I said, there's no point in having a circuit breaker that's not going to trip when you've actually got a high level short circuit. What is the point of that, and you're going to have possibly cables fusing off and a huge amount of damage probability on the site. So that takes care of two of the types of settings. There are a number of other settings which we'll get to in a more practical way of having a look at these, but these are the basic rules that we need to have a look at. Then finally, we need to look at the timing elements of these. So all adjustments have current, they have actual values for short circuit, they have a number of timing elements within the curve settings. Now, we can have a look at these, and they will traditionally will be set on maximum. The timing setups are those which are going to sort of modify the middle of the graph in terms of overload values and also some short circuit levels in terms of timing. So mixed or resistive loads tend to not have high inrush values, and we could easily set these somewhere between the minimum value and the mid-range of those adjusting knobs. If you've got motors, for instance, you would tend to put them from the middle of the range to the max. Now, the only time you'd probably use the max is if you've got a single motor and nothing else on there, a single huge inrush value type of thing. So if you don't really know, I suppose you could spot them and put them in the middle anyway. The idea here is always that under running conditions that they would never trip with nuisance values that you need to have a look at. Some breakers have specific ranges that you have where they cancel out 1, 2, or 3 cycles, specifically for motor type use. So you need to understand those timing circuits which sort of delay the trip under certain conditions. They might have a dual rating. So a breaker like that might have a rating that you'd use for more resistive load on one scale and another scale for motors. So you'll see some activity in the next slide batch where we actually have a look at 2 of the breakers on the market where you see that type of thing. And then point 4, step 4, there's obviously electronic breakers offer you a huge amount of additional benefits. Now here I'm talking about things like phase failure, phase rotation, LED warning lights, excuse me, and the rest of the features that you could have where you've got those values on your actual settings, and you need to understand what you've got there as you set them. You might have options to set, for instance, an LED base which says when you exceed 80% or a value that you can preset, we might call it 80%, where the little LED bar graph changes color, warning you that the product's about to trip or in the zone of close to the tripping point or the maximum value. So that's, in a nutshell, the 4-point system that we would use to make sure that all electronic breakers are preset when you need to do them on site. So if we have a look at that, we must understand the circuit breakers is required to trip at the speed of what that short circuit is. So the higher the actual short circuit value, the faster the breaker should trip. And that's fundamental to all the circuit breakers, and that's an inverse tripping characteristic. So that forms the end of the basic discussion on the actual setting of the breakers. And if you follow on the video where there's actual examples used, you'll actually get to have a look at what the dials mean and what the values are, and then get some idea of what you need to adjust on these two particular breakers. And thanks so much.